Hi, I'm Dr. Neenungar. In this session, I will discuss deadlocks. Let's start. What are deadlocks? In real life, when two trains approach each other at a crossing, both shall come to a full stop, and neither shall start up again until the other has gone. It takes money to make money. So you need money to make money. No money, no more money. Deadlock. You can't get a job without experience. Also, you can't get experience without a job. So these are some real life examples that are related to deadlocks. Now we will discuss deadlock in terms of processes. Now what is the deadlock problem? A set of blocked processes, each holding a resource and waiting to acquire a resource which is held by another process. If there are three processes, P1, P2 and P3, P1 is waiting for some resource which is held by P2. P2 is waiting for some resource which is held by P3. P3 is waiting for some resource which is held by P1. So all these three processes, P1, P2 and P3 are blocked processes, and each of these three processes are waiting for other processes. So this is a deadlock. Let's take another example. A system has two tape drives. P0 and P1 is holding one tape drive. P1 has one tape drive and P2 has one tape drive. P1 needs two tape drives to complete its execution. P2 needs two tape drives to complete its execution. What will happen now? P1 is waiting for P2 to release this tape drive. P2 is waiting for P1 to release this tape drive. So this condition is a deadlocked condition. It is a deadlocked condition and the processes are said to be blocked or deadlocked. Okay. Now next example, semaphores. You must have covered in synchronization semaphores. Okay. Now there are two semaphores A and B. A equals to 1 and B equals to 1. Now what has happened? Process P0 has generated a wait call on semaphore A. So the value of A becomes 0. Now process B has called wait B. So it is B equals to 0. Okay. Now process A wants to call wait on process B. But it has to wait because the value of B is already 0. So it has to wait till P1 issues signal B. Similarly, P1 wants to take hold of semaphore A, but A is equal to 0. P1 will wait till P0 issues signal A. But now this event is possible, signal B event is possible when P1 will get A. But P1 cannot get A because P0 has issued wait A. P0 has issued wait A and it can only execute when P1 will issue signal B. So in terms, both are waiting for each other to release the locks. So these two processes are in deadlock. Okay. Now let's see another example, which is bridge crossing example. Suppose this is a bridge and on this bridge only one car can go in one direction at one time. This is car A and this is car B. At one point of time, both A and B are on the bridge. B has to go in this direction, A has to go in this direction. but both are stuck. One of the car has to roll back so that another car can pass, after which B can pass. So what we can say, if a deadlock occurs, it can be resolved if one car backs up. It means in terms of processes, if it releases all the resources that it has or its resources are preempted and it rollbacks. Now in this diagram, there is just one car is shown which has to be rolled back, either A or either B. But what will happen if so many cars are in line? So for either of the for either of the car to pass the bridge, all the cars on the opposite side have to roll back. So several cars have to be rolled back. So in terms of processes, it is possible that to avoid deadlock, many processes have to roll back. It is not like only one process rollbacks, the things will be okay. It could be like many processes have to roll back. In this case, what can happen? Starvation is possible. How? There can be some process which is waiting to execute, but it never gets all the resources that it needs. Now let's understand the system model of a deadlock. A system consists of a finite number of resources. The resources are finite. And these finite resources are to be distributed among processes. Now, under normal mode of an operation, a process will first request for a resource. Okay? And if the resource is not available, then it will wait until the resource is available. Next, suppose the request is granted, the resource becomes available, and the resource is granted, request is granted, and resource is allocated to the process. The process will then use the resource. Okay. Now, once the process has used the resource, it will release the resource. It will release the resource. In deadlocks, processes never finish execution and the system resources are tied up, which prevents further jobs from starting. Before we discuss various methods that can handle deadlock, let's first discuss the conditions that characterize deadlocks. So there are 4 conditions. If these conditions hold simultaneously, then your system is in deadlock. So we will first discuss the first condition, mutual exclusion. According to this condition, only one process at a time can use a resource. It means the resource is non-shareable. So if in your system there are resources which are non-shareable, then there is a possibility that the system might go in deadlock. But this is obvious. There are some resources in system which are always non-shareable, like printer. A printer is non-shareable. It will print the output for one process at one time. Okay, it will not print several outputs for several processes at one time. Another is if there is any file which is open and it is in writable mode. So it is by default non-shareable. So you cannot prevent this condition to not to occur. Second condition that is necessary for deadlock is hold and wait. As the name suggests, holding something and waiting for something. So it means in your system, a process is holding at least one resource and it is waiting to acquire additional resources which are held by other processes. If this condition occurs in your system, then deadlock may occur. This is another necessary condition for deadlock to occur. Next is no preemption. No preemption means, as the name suggests, resources cannot be preempted, which means a resource can be released voluntarily by the process which is holding it after that process has completed its task. You cannot simply preempt the resources. Okay. Next is circular wait. Circular wait means there is a set of processes in the system which are waiting, and the wait is circular. Like P0 is waiting for P1 to finish, P1 is waiting for P2 to finish, P2 is waiting for P3 to finish, and P3 is waiting for P0 to finish. So every process is waiting for the other process to finish. Finish means P0 is waiting for some resource held by P1. P1 must be waiting for some resource held by P2. P2 is waiting for some resource held by P3, and so on. If this type of circular wait exists in your system, then this completes the necessary and sufficient condition for deadlock to occur. If all these four conditions hold simultaneously in your system, then a set of processes is definitely in deadlock in your system. We know that the four conditions are mutual exclusion, hold and wait, no preemption, and circular wait. If these three conditions exist in your system, then there is possibility of deadlock. There is no assurity. But yes, there is possibility of deadlock. But if these four conditions occur, then there is existence of deadlock. Why? Now, we have already discussed that these are necessary conditions, but let's see, these are not sufficient. Mutual exclusion. As already discussed, there are some resources which will always be non-shareable. So you cannot control this condition. This is necessary condition. Hold and wait. P1 is holding a resource R1 and it is waiting for some resource which is held by P2. R2 is with P2 and P1 needs this resource R2. But it is possible that P2 finishes its execution. It is not necessary that P2 is also waiting. It might or might not be waiting. So if there is any process which is holding a resource and it is waiting for other resource, then there is possibility of deadlock. However, there is a chance that it can get the resources for which it is waiting. So it is a necessary condition, not sufficient. Next, no preemption. Resources should not be preempted just arbitrarily. So it should not be the case that if a process is not able to execute, then simply preempt its resources. It should not be always done. It is not always a desirable solution. But yes, if there exists circular wait along with all these conditions, again, consider the example. In this case, P1 was waiting for P2, but P2 was not waiting for P1. P1 may or may not was waiting for any other process to finish. But now I am saying, yes, P1 is waiting for P2, and let's say P2 is also waiting for P1 to release this resource, R1. Now there is a circular wait. Each of them is waiting for each other to finish. So these two processes, P1 and P2, are deadlocked. Initially, there was mutual exclusion. R1 and R2 were mutually exclusive. They are not shareable. Okay. Hold and wait. P1 was holding something, P2 was holding something, and both were, P1 was waiting, P2 was not waiting, may or may not wait for some other process. Okay. No preemption. These R1 and R2 are not preempted. We are not preempting these resources. These are non-preemptible resources. It can be some file in open mode, in writable mode. So it cannot be preempted just like that because the data is in inconsistent state. It is very important to understand that resources are not just physical resources, these can be logical resources as well. So when there is circular wait, it completes the necessary and sufficient conditions of deadlock. Now these two processes are in deadlock. So in this session, we understood that a set of processes is in deadlock state when every process in the set is waiting for an event that can be caused by the other process in the set. Okay, I hope you understand the basics of deadlocks. Thank you.